Good morning. Today's topic is sampling theorem. You might have already studied this one in your last semester in the Signals and Systems course. But let's have a quick recap of what actually sampling theorem is. Now we are into the digital list. As we have already discussed that the conventional signals are basically analog signals, and you are supposed to convert them into digital signals in order to process them for analysis. So this conversion of analog to digital signals require sampling of the data, and here comes the sampling theorem. So we'll have a quick look at the sampling theorem, and we will see what actually aliasing effect is. So this is in continuation with your previous topic which we have discussed about analog multiplexers and digital multiplexers. So this is linked with your analog to digital conversion. Now I hope that by the end of this video lecture you will be able to describe the sampling theorem, why it is so important, and in particular about the aliasing error in the signals. So let me start with the sampling theorem. The sampling theorem states that a band limited signal can be uniquely specified by its sampled values if and only if the sampling frequency is at least twice the maximum frequency component contained within the original signal. Now let us suppose you do have a signal of f of t which is represented in terms of f of omega. Now let us suppose it is represented as 2 sine omega t. So which means that the sampling frequency will be somewhere around omega. This is the maximum frequency component contained within the original signal, and your sampling frequency must be greater than twice of this omega. So in this case it is, so you can choose sampling frequency like 3 omega, 4 omega, 5 omega like that. Now let us suppose if you do have a signal of now in this case, if you see the maximum frequency component here is 6. Let us suppose I take it as 2 omega and 6 omega. So the maximum frequency component is 6 omega. So in that case, your sampling frequency must be greater than twice of 6 omega, which means that your sampling frequency must be greater than or equal to 12 omega, not this 4 omega. Okay. So this is if you select the sampling frequency such that it is greater than or equal to twice the maximum value of the component in your waveform, then sampling will be perfect. So the frequency component at half the sampling frequency is known as Nyquist frequency. What you call it as Fn. Try to remember this formula. Fn is equal to Fs by 2. Now, the sampling process is effectively achieved by connecting an analog signal to the data acquisition systems by means of a fast acting switch which closes for a very short time but remains open for the rest of the period. So this operation can be modeled by a multiplier, where f of t is a band limited analog signal to be sampled and s of t is considered to be the sampling function. Now the sampling function is somewhere varying between 0 and 1 and it is defined as follows. So it is just like the sampling function is defined as, let us suppose this is time. So it is defined like this. Which means that most of the times it is 0, but for shorter durations it is 1. And it happens at regular intervals. This is called as a sampling time. Most of the times in textbooks you will be seeing that they will be starting from 0. So it is. So sampling time is the duration between two successive samples. Now, Your original function is f of t, and now your sampler, whatever which you are picking up, it is having, you are going to pick n number of samples. Now, the function is represented in this fashion. This is your sampler, and this is your original function. So, if you multiply these two, then you will get your resultant digital function. So, it is nothing but just like if you are having this is your f of t, it is like this. This is your f of t, and this is your sample. Let us suppose so. The resultant value will be so the resultant value will be like this. So this is a true representation or an approximate representation of your continuous time signal. And this is a discrete time signal where the value has been stored only at regular intervals, which you call it as a sampling time. Now, if you carefully see, if you want to have more number of samples, then it is good because it reflects a true waveform. But the problem is that if you are going with a smaller sampling time or a large number of samples, then automatically the system may become complex. That doesn't mean that you are supposed to go with 2 or 3 samples only. So choosing a right number of samples is one of the most important things. And see, coming to mathematical model. Now this is your original function and this is your sampling function, and I am multiplying. So if you want to bring it to this one, then you will convert it into t is equal to nts. So I am converting into this one. Now, this is your original signal, and this is where you are picking up your samples. So if you multiply these two, then this is your out representation. So which means that you are getting a true replica of your waveform, an approximate most of the times. Now, if you see it, this is your time domain representation. Now, if you want to see it as a frequency domain, then it is assumed that this particular wave, whatever which you are choosing, it is having a frequency components which are not beyond omega n. Okay, I am assuming that the maximum frequency component is omega m only. So this is the frequency representation. With respect to frequency, how the magnitude is varying. Now this is the sampling one in terms of frequency. So now if I join them, then this is my output. This is what is being represented here. Understood. This is the sampling process, how we do. This is with respect to time, the samples. This is with respect to frequency. Now, if you see, the sampling function consists of a train of pulses which are spaced equally by the interval Ts. The choice of Ts is yes. If you want more number of samples and a very exact replica, then you can go with a smaller sampling time. And the amplitude of each sample is same as that of original signal at that particular sample time. Okay. And the resulting samples are included within the original signal envelope that we have seen here. These are the final samples now. They do represent the exact magnitudes at that particular interval time. So, and coming to frequency, this is recording the time domain, and coming to frequency, it is assumed that the function contains no frequency above omega. And this is the fundamental thing which we basically assume. That's why before this before converting into digital multiplexer, that's why what we do go with LP filter, where we do eliminate higher order harmonics, and we will limit ourselves only to lower order frequencies. So based upon that assumption, I'll take that my signal doesn't have any frequency which is higher than omega m. So the spectrum now, If I convert it into frequency, now this is my representation. This is my sampling function, where this is your sampling frequency. Right. Now, see, I'll show you one particular thing. See, this is the relation between the sampling time and the sampling frequency. They do have an inverse relation. Now, in accordance with the convolution theorem, now you do have two signals. Now, one is your f of omega. This is your initial one, and now you are having a sampling function. Now you want to convolute between these two. In terms of convolution theorem, when both are represented in terms of frequency, then what you can do, you can directly multiply them over the time period. So this is fs of omega, the resultant value is going to be 1 by 2 pi f of omega into, this is the sampling one, and this is the original signal. Now the convolution, now if you carefully see, it produces fs of omega displaced in frequency steps. This is what I have shown here. Yeah, this is here fs of omega, and this is here s of omega. Right, so this is f of omega, and this is the resultant one. Okay. Now, one more thing. It is important to note that there will be no overlap of adjacent points as long as this one. Now I'll show you what happens actually when we do pick these type of things. Now let us suppose this is my original signal, right? Okay. Now, see here, what is this is the entire periodicity of my signal, right? So what is my frequency now? It is 1 by 6. Right. Now what I should do, let us suppose if I take a sampling frequency which is less than, I'll take case A, which I'll take it as fs is less than twice of omega. Here my maximum frequency, I do have only one particular signal, and it is 1 by 6. So I'll take anything less than 6. So what I'll do is nothing but I'll take 1 by 12, which means I'll take, let me do one thing, let me take what I'll do is that yeah, this will be a better thing. Yeah. Now let us suppose this is my original signal f of t. Okay. Now this is my frequency. Now let us suppose if I take it as 5, this is 10, this is 5 milliseconds, this is 10 milliseconds, this is 15 milliseconds, and this is 20 milliseconds. Okay, which means that my time period is 10 milliseconds, and my the signal frequency is 1 by 10 milliseconds, and it is somewhere around 100 hertz, right? Now let us suppose case A, if I take fs is less than 2 of 100, which means that I'll take fs is equal to 100, which is less than the predefined value of 2 into. Normally what I should do, my case is fs must be greater than or equal to 2 into 100, which means fs must be greater than 200. So what I'll do is nothing but I'll take three options. I'll take less than 200, I'll take equal to 200, and I'll take 300. Now we will see. Now the first case what I have done is nothing but fs is equal to 100. If fs is equal to 100, sampling frequency is equal to 100. So what samples I am supposed to collect now? My sampling time will be 1 by 100. So what I will be getting? I will be getting 0.01 seconds, which means 10 milliseconds. Every 10 milliseconds I am supposed to collect a sample. So what I will be getting here? This is at 0, and this is again I will be getting at 0, and again what I will be getting? I will be getting again a signal like this. So if I join these signals, do I have any output? No, I don't have any output here. This is the problem, which means that it is just like a straight line, right? Now let us suppose if I take something like 50, right? So I have to take 50. So it is 1 by 50, it is 0.02 seconds, which means 20 milliseconds. So what I'll get directly here. So this is at 0 and this is at 0. This is not a replica of what actually we have desired. Understood. Now case 2, I'll take Fs is equal to 200. What happens if I take same? So if Fs is equal to 200, what is my sampling time? It is 1 by 200, it is 5 milliseconds, which means I am going to take signals at every 5 milliseconds. So what I'll get again? I am getting again 0, because at 0, 5, 10, 15, 20, if you carefully see, the values are again 0 itself. So my output will be just like this. This is also not what I have decided. So what I should do is nothing but f of s is greater than 200 I am picking. So I am picking as 300, or I will take 400. So if it is 400, what is my sampling time? 1 by 400, it is 0.25. Sorry, 2.5 milliseconds, right? If I take it as 2.5 milliseconds, which means that what are the samples which I am considering? 0, 2.5, 5, 7.5, 10, 12.5, 15, and again 17.5. Now if you carefully see, at 0, it is value 0. At 2.5, then I will be getting, at 5 is 0, at 7.5 it is somewhere like this. Now here again, so at least it is somewhat better when compared to the previous one. So this is an approximate representation of a sinusoidal signal. So if you go on increasing the frequency, let us suppose if I take sampling frequency as 800 Hz. So it is Ts by 1 by 800. What I will be getting? I will be getting 1.25 milliseconds, which means that I will be getting somewhere here also. Now this is very clear. It is somewhat close to your sinusoidal signal, right? So the higher the sampling frequencies, minimum value must be greater than 2 times of your maximum component of the frequency. Otherwise, this is the problem which you will be facing. And next is, I'll show you one more example. Now let us suppose my signal is equal to 3 sine, I'll take it as I'll take this. Alright, I'll take this. Now let us suppose this is a signal which is having somewhere around 5 milliseconds. This is 10 milliseconds, and this is 15 milliseconds, 20, and this is 25, and this is 30. Okay. Now see the sampling frequency, the frequency here in this case is 1 by 10 milliseconds, 100 Hz. So my signal is omega is equal to 314, right? Isn't it? Now what is my function of this one? F is equal to, now let us suppose if I take maximum value of this one as 5, its value is 5 sine 314t. Now let us suppose if I I'll assume that it is having a third harmonic component also, 3 into 314, which means that there is another signal which is included in this one. See, and that is having okay. So it is like this. Actually, these are all sinusoidal, but I am unable to draw them. Okay. Now, okay. So if it is not correct, let me draw it again. Okay, this is 1, right? I'll take it as 10 milliseconds. Sorry, 5 milliseconds and 10 milliseconds. Now I'll take another one. Okay, now if you carefully see, it is having two signals. This is a primary signal which is having a frequency of 100 hertz. Okay, so that signal is 5 sine 314t, plus there is another signal which is having double the frequency. Right, so if I join these two signals, then what is my resultant signal? How it will be? It will be like this. Right, so now how you are going to choose your sampling frequency? If you choose your sampling frequency as 100, so in this case, what is the maximum frequency? It is 200, not 100, because this is having a higher frequency. So how you should choose your sampling frequency? Greater than or equal to 200. Sorry, 2 times of 200, which means you are supposed to go with at least minimum of 400 hertz. So in this case, what I should do? I should go with 500 hertz, right? Which means 5 times. So within this, I am supposed to take 10 samples here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is you are supposed to do. This is how you are supposed to take samples. In the previous slides, we have seen that anything less than 2 times of maximum frequency, then you won't be getting a proper replica of your signal. And this is called as signal aliasing error. Okay, so it will be difficult to distinguish between the components, different components. Okay, for further reading, we will discuss further more in the class. See. Okay, so sampling theorem essentially says that a signal has to be sampled at least with twice the frequency of the original signal. And since signals and the respective speed can be easier expressed by frequencies, most explanations are based on the representation in the frequency domain itself. Okay, so I hope that you are able to describe the sampling theorem and what actually is an aliasing error, which happens when you are sampling the signals. Okay. For more discussion, go through the textbook SLS and come back to the class. We'll have a quick discussion and how this sampling theorem is to be implemented. Okay, thank you.